Okay, so I think we're going to go back now and pick it up where we left off. Actually, we're in 3B right now. And so what I wanted to do is go back and start again with this concept of concavity. So we want to remember now that we're thinking about optimization in the sense that we're looking for minimum and maximum points for a function. And we've discovered that one way we can find them is to look for points where the first derivative is equal to zero, because that means that the tangent line to that point is horizontal and therefore has a slope of zero. What we have to do too, though, is confirm these points that we've discovered, whether they're maxima or minima, because the tangent being zero there just means it's a relative extremum. It doesn't by itself prove whether it's a maximum or a minimum. For that, we need more information. So one thing we can do is inspect the sign of the first derivative on either side of that point. And as you can see from this graph, if the first derivative goes from positive to negative around that point, it must be a relative maximum. Or down here, you can see the opposite. We go from a first derivative that's negative up to positive on either side of this point, and that tells us this is a relative minimum. Now with concavity, we're looking at the second derivative. Okay, so we're assuming that our function is differentiable over some interval, meaning there's no discontinuities or sharp breaks. And if it turns out that over that entire interval, the first derivative is always positive, then the function is defined as being concave up. Okay, so you recall we went through these diagrams very extensively. Concave up occurs in this first graph in the upper left-hand corner, because you can see that the slopes that they put in, it's a little faint, but those little red lines are the slopes of tangents at those 2 points. And you can see that they're always going to be positive. So at least within this interval, the function is concave up, right? And then we can see down here directly below it, it's the same thing. So even though the slopes are negative, as x increases, as we go from left to right, you can see the slope is becoming less negative, which of course is the same thing as becoming larger. And so therefore, this one also is defined as being concave up. Okay. By the way, I just want to mention in terms of terminology, concave up sometimes is referred to as being convex. Okay. It I don't know how this happens or how the notation or the terminology can get to the point where there's so many different ways of describing the same thing. But if you've heard the term convex, this is what they're describing. On the other hand, we have concave down, which is simply called concave in some books. And what's going on there, of course, is the opposite case where the second derivative is negative throughout that entire interval. As you can see, in other words, it's shrinking. As x increases, the slope is decreasing. And that means that it's either becoming less positive or more negative. Either way, as you can see in the 2 graphs on the right, the function is said to be concave down. And again, the whole idea here is that with concave down, the second derivative is negative throughout that interval. With concave up, it's positive. And then we can use this information to help us identify maxima and minima in a slightly different way. We already have seen the first derivative test. Now we're going to introduce the second derivative test. And by the way, here's a geometric interpretation of convexity and concavity. You look at these 2 graphs. What do they have in common? Well, you can see that as we go to the right, let's sketch this in here. The slopes of these tangent lines are increasing. In this case, they're becoming more positive. In this case, less negative. So we know that the second derivative in both cases is positive. Okay. Okay. And so that's how we know that these 2 functions, at least again over that interval defined by these 2 endpoints, are concave up, or sometimes they're called convex. So the geometry comes in where what we're doing is we're defining a secant line through the two endpoints. And if you notice, the secant line is always above the function in both cases. And so that's how we know, in terms of geometry at least, that the function is concave up or convex, which means that, of course, in the opposite two cases, you can see these are concave down. And again, the whole idea here is that slopes here are becoming less positive. Over here, they're becoming more negative. And that tells us once again that the second derivative is negative in these two cases. At least over these intervals. Means that they're concave or concave down. Okay, so by the way, you do sometimes run into functions that are convex or concave throughout the entire function, but we can define it over a specific interval. And so we're going to test, first of all, we're going to check for concavity or convexity. And so f of x is, of course, a function that must be twice differentiable over an interval, no discontinuities, no breaks. Then, as we've just seen, as long as the first derivative is positive for all x's in that interval, then it is said to be concave up or simply or convex. And then down here, this is concave down is sometimes simply referred to as being concave. And that again is a result of the negative second derivative throughout the entire interval. Now, we have this interesting concept called an inflection point, which is a point where the concavity of a function switches from either up to down or down to up. Okay. So like here's a good example of this. You can see from in the first region here, call this region 1, and let's say region 2 over here. Within region 1, you can see the function is clearly concave up. Okay. The second derivative is positive because the slope is going from negative to 0 to positive. We have the positive second derivative, and that means within this interval, let's say this is the beginning of our interval, we know that the function is concave up. Now, we hit this point, A, where all of a sudden, look what happens. After that point, the slopes are becoming positive, 0, negative. And that means within that interval, the function is concave down. So the point where they switch from one to the other is called the inflection point. Now you might say, well, all right, that's interesting, but what are we supposed to do with that information? Well, it'll help us identify, depending on what test we're using, our maxima and our minima. Okay, so let's take a look. Now, this is, of course, a polynomial. It's a cubic function. Let's determine all the intervals where f of x is concave up, down, and identify the inflection points. And by the way, there don't have to be any inflection points. Like if you had, for example, something like this. This is some parabola, y equals, let's say, x squared minus 2. And if you look at it carefully, the slopes are going from less negative, 0, positive, and positive. So that means this function, oh, what happened? It erased what I wrote. I didn't even notice. Okay. So x squared minus 2. So this one is concave up throughout the entire function. In other words, there are no inflection points. Now, we could have determined this in a slightly different way. Using the power rule, we could have determined that the derivative, say we wrote this as f of x equals x squared minus 2, f prime of x based on the power rule would simply be 2x. Okay. The second derivative is just 2, which is guaranteed obviously to be positive. In other words, there's never going to come a point in this function where the second derivative is not positive, okay, because it's just simply 2 throughout the entire function. So here, there's not going to be an inflection point. And the same thing would be true for a downward facing parabola, where it would be concave down throughout the entire function. So there's no guarantee that there will be an inflection point. But if it's there, we want to know how to find it. Okay. So here's the function we're considering. And it's kind of it's cubic, and it has that traditional curve. Cubic functions tend to be curved in a specific way. And you can see we do run across a relative maximum because the slope of the tangent line is 0, and a relative minimum. But how do we know which is which? Okay, and then while we're at it, how do we know what's going on with the inflection points? So now sometimes it's hard to tell just by looking at a function like this. But visually, if you look at it, it appears that while here the slope is going from positive to 0 to negative, it appears, again, it's kind of hard to see unless we really zoom in on it, that at some point, though, we're going to go from negative to 0 back to positive. So there's a point in here where the concavity changes. Over here on the left-hand side, second derivative is negative. Okay. Because it's going from positive to 0 to negative, meaning concave down. On the right-hand side, it's the other way around. Now, here's an interesting question. How do we identify this point? Well, at the very least, we're going to have to take the second derivative of this function and set it equal to 0 and see what happens. Okay. So let's do that. Let's take the first two derivatives. Now, this is a straightforward polynomial. We're going to apply the power rule to each of these terms. And of course, you recall that the derivative of a constant is just 0. So we'll get, for our first derivative, 3x squared minus 12x plus 9. And then when we reapply our power rule, we get 6x minus 12. So what happens if we set this equal to 0? X equals 2. So that looks about right. Based on this graph, you can see it. Oh, you can't really see it that well, but it's almost, they're trying to show it like on a piece of graph paper. And it's kind of faint, but it appears that this is 2, since this is 0 and this is 5. Or actually, I'm drawing it in the wrong place. Sorry. Let me fix that. Right there. Now we can figure out the y value if we need to, just by plugging in 2 to the original function. It's not always necessary, but if we do, we get 2 cubed minus 6 times 2 squared plus 9 times 2 plus 30. So we have 8. Now here we have 6 times 4. 32. Okay, so that point, 232, is our inflection point. Okay, so in other words, this is where the second derivative goes from negative to 0 to positive. And so in other words, we're changing from concave down to up at that point. Now, now, of course, if we don't have the graph in front of us, what we can still do here in order to determine which region is concave up and which is down, what we can do instead is look at the sign over those two intervals. In other words, remember, we determined that f double x double prime of x is 6x minus 12. And so what we can do is say, well, listen, we know that whatever this, let's say that we don't have symbol lab at our fingertips, and we're not completely sure what the graph looks like. Well, we do know that the point 232 is our inflection point. What we don't know is which of these two sides is concave up or down without testing them. So over here, let's just arbitrarily pick one, because one is definitely in that interval, and find out the value of f double prime of 1. Okay, so this one is negative. And we know that a negative second derivative indicates that the function is concave down. Okay, as we see in this graph. Okay, so the left-hand side looks something like this. So let's check the right-hand side. And we can pick any value in this interval. Let's just pick 3, let's say. Okay, so we have our results. That means this region is concave up. And this one is concave down. So if you had to sketch it, you would say, well, it's going to have to look something like this. Sometimes it's not that easy to sketch a function without more details, but the idea here is that it has to at least show that it's switching from concave down to up. Just like you see here. So this is our inflection point, and it separates the area in which the graph or function is concave down from concave up. So now, by the way, yeah, this is just a little reminder how the first derivative test works, that we know that our critical points occur when the first derivative is equal to 0, which means they could be maxima, minima, or possibly neither. So we can check by looking at the signs of the first derivative on either side. And if they go from 0 to positive rather to 0 to negative, that's a sign of I'm just putting these little arrows to indicate that it's go next. This pattern from positive to 0 to negative indicates concave down. And the opposite pattern going from negative to 0 to positive must mean concave up. Okay, so again, you can see by looking at this, it's normally the case, of course, as you know in calculus, that we can get the same results with many different techniques. So the second derivative test formally refers to the way we find extrema rather than the inflection point. What we're going to do is this. We're going to follow that pattern we just saw. If we find, first we identify our critical points. Okay, then we test them with the second derivative. Now, what is this doing for us? It makes it unnecessary to calculate all these first derivatives and compare them to each other. So it could be a little bit faster because we only have to do one thing. Once we know what our critical points are, instead of testing the signs of the first derivative on either side, we can just go ahead and calculate the second derivative. And if the second derivative is positive, then this must be a minimum. Like here. go back to one of the earlier graphs for a second. Yes, in other words, this by itself, we can figure out from this information, assuming that this is, of course, a critical point. We have to demonstrate that first, that it's a critical point. Then once we know that, we can test whether it's a relative maximum or minimum by looking at its concavity or second derivative. All right, so obviously the opposite would be true if the f double prime is negative, which you're going to find, where were we? Here. In that region, the second derivative is negative, and that implies that this point, this critical point, call it, let's say C1, and this one could be C2. That must be a relative maximum. Now, there's only one complication. What happens if the second derivative is exactly equal to 0? Then we don't know. It could go either way. We call it inconclusive. Or it could still be neither. Okay, so in other words, we need to do something different if it's exactly equal to 0. All right, so let's try this. Oh, now look at this. This is a fifth order polynomial. So we're going to take the second derivative. Let's try that right here. First derivative, based on the power rule, will be 5x to the fourth minus 15x squared. And the second derivative will be 20x cubed minus 30x. Okay, now that by itself is still a very complex function. So now, oh my God, now this is what it looks like. And so what we have to do is first find the critical points, as we always do, by setting the first derivative equal to 0. Now this one, you can see the first derivative is a fourth order polynomial. I think it's called a quartic equation when it's to the fourth power. But the bottom line here is that you're going to find that you're going to have quite a few solutions, and so possibly up to 4 of them, where this derivative crosses the horizontal axis. In fact, I'll tell you what, just because it might be interesting, why don't we graph in Symbol Lab this first derivative? Okay, because what we're looking for is the points where it crosses the horizontal axis. So we'll have 5x to the fourth whoops, nope, minus 15x squared. All right, so let's just take a look at this thing. So you can see it does cross 3 times. It's a very strange little graph. It crosses 3 times, and according to Symbolab, they are, looks like 0, 0, radical 3, 0, negative radical 3, 0. Okay, so those are going to be our 3 critical points. Now we can do this algebraically. Imagine, we don't have Symbolab in front of us. What we did was first factor out 5x squared. Okay. And then we also then have that multiplied by x squared minus 3. And that means that each of these individually is equal to 0. This one we can solve by adding 3 to both sides. And we end up with, as we predicted, plus or minus radical 3. So the critical points are 0, 3, and negative 3. 3 of them, as we saw before. Now, what we have to do now is solve for the second derivative at each of these 3 points. What we're looking for is positive, negative, or 0. Oops. All right, so let's do this. So we try it when x equals 0, and we get 0. So the test is inconclusive when x equals 0. What about plus and minus radical 3? Well, here's negative radical 3, and you can see it's negative, which implies that this point is concave down. Okay, so here we have concave down, and here we have concave up. So what this means then is that we have, when x is 0, the second derivative test is inconclusive. Here, positive, we have a positive second derivative, which makes it a local minimum. Okay. By the way, when it is concave up, of course, it is going to be a minimum because it's basically the bottom of a valley, I suppose you could call it. And then this one has to be local maximum. Okay. Now, what do we do about that 0? Oh, see, now you can see from the graph, it makes sense what the results we got. You can see that this one is neither a minimum nor a maximum. Ah, so we've seen already that critical points are not necessarily always associated with maxima and minima. Just because a point is a critical point, it doesn't necessarily mean that it's a minimum or a maximum. And that's what happened here. We have a maximum here, of course, and we have a minimum here. And you can see, I mean, we do have a tangent with a slope of 0, which means it is indeed a critical point, but it didn't turn out to be either a maximum or a minimum. So now, by the way, when you run into this situation, we're not going to see this just yet, but if you think it might still be, or you're interested in knowing what it is, you can actually try higher order derivatives until you find a result. And that would tell you what you're looking for. We're not going to do that here, but in other words, you don't just give up. You can try by going on to the third derivative test, and then the fourth and the fifth until you get a result, which is not 0. All right, so that was the end of 3B. Now we're ready for 3C. Now 3C is kind of an interesting topic because we're bringing back our old friend limits, but in a very interesting way. You might recall with limits that we found that most of them were pretty straightforward. You can substitute the value that we're converging to into the functions, and we come up with some number. The problem is what happens when you get division by 0 or something like that. Well, it turns out there's a bunch of rules that we can apply in those cases. Not every one of them, but there's rules that can help us with these oddball situations that arise from time to time. Like this one, for example, I've got the quotient of two functions, and I want to know the limit as x goes to a. Now, what if it turns out that the functions were something like, I don't know, let's say 2x minus, let's see, 2a. And this one is 3x minus 3a. If I plug a into that x, I'm going to get 0 over 0. So this is referred to, by the way, as an indeterminate case form, 0 over 0. When you run into 0 over 0, you might be tempted to panic. But this is why we have our friend L'Hopital's rule. Now, L'Hopital, obviously, it's a French name. There's actually a missing accent here. And L'Hopital, of course, is a mathematician who invented this rule. And basically, it's a very straightforward rule. When you run into the 0 over 0, here's what you can do. It turns out the limit as x goes to a of f of x over g of x equals the limit as x goes to a of f prime of x over g prime of x. So if we take the derivatives and we do not have 0 over 0, then we have our limit. Okay. Now, sometimes it works and sometimes it doesn't. But when you see 0 over 0, your first instinct should be try L'Hopital's rule, take the derivatives and see what happens. All right. So here's one. Now, substituting 0. Um, okay. Oh, I have to get my calculator out. Hold on. The cosine of 0, you can memorize this stuff, but anyway, I'm gonna find this on my phone, my calculator. There's actually, if you're not familiar with this, on your iPhone, there is a very powerful scientific calculator on there, but you have to remember to turn it into landscape mode. Otherwise, you're just going to be using a very basic one. This is the powerful one, and you can see it does have all the trig functions. So the cosine of 0 is 1. Okay, so that means when you substitute, oh boy, here we go, 0 over 0. So that means L'Hopital's rule. So, and yeah, here's the function. You can see what's going on here. And you notice there's a hole in there. Yes, of course, there has to be a hole because x can't be 0. The domain cannot include 0. So the question is, what is the limit as we approach this point from either side? Okay, so what do we do? Here we go. Let's take the derivatives of the numerator and the denominator. So remember from way, way back, so when you take the derivative here in the numerator, this derivative is 0. This one will be negative sine x. So in the numerator, you're going to end up with positive sine x. In the denominator, the derivative, of course, of x is just 1 based on the power rule. So if you plug that in, if you go back to your calculator, the sine of 0 is 0. And that's exactly what you would have expected after seeing this graph. You can see that while there's a hole in the function, the hole is at 0. So in other words, approaching from the left to the right, the value of the function at that point approaches 0. So because it's the same coming from both directions, even though there's a discontinuity in the function, then there is a two-sided limit. There's a left-hand limit, right-hand limit. Therefore, there is a limit, and that limit is 0. Interesting. Oh my God, look at this one. Now, what happens if you take the limit of just this term? What's happening is this x is growing to infinity. Okay. And then, the same thing here. Yeah, just wondering for x. So the way you have to think about this is that if you're dividing by a number that's getting extremely large, so large that it's getting close to infinity, this reduces to 0. So the limit of 1 over x as x goes to infinity is 0. And if you're not sure, you can just remind yourself. So as we move in this direction, you can see that we're heading towards zero. Okay, this because the horizontal axis is an asymptote. So the limit as x goes to infinity, this function is defined as zero. So when you make these substitutions, you'll end up with 1 minus 1 over 0, which is of course 0 over 0. And now that means again we're ready for the L'Hopital's rule. Yes, and this is what it looks like. All right. And yes, as I mentioned, as x goes to infinity, this ratio goes to 0. Direct substitution leaves us with 0 over 0. And now we differentiate the numerator and the denominator. Now, let's do e of x requires the chain rule. Okay, so that means let's rewrite this as x to the minus 1. It'll be a little easier to see what's following. By the power rule, the derivative of x to the minus 1 is minus x to the minus 2 power. Okay, now this one just goes to 0. In the denominator, as we just saw, the derivative of 1 over x is negative x to the minus 2 power. So what do we end up with? Plugging them in the numerator, we have e to the x to the minus 1, or e to the 1 over x. And then this part just goes to 0. And then wait a minute, where are we? Yes, so in other words, this result from up top here, just the e to the 1 over x, could be rewritten. Looks like it got rewritten in the next slide. It's minus e to the x minus 1 over x squared. So I just want to make it clear when you look at this next slide, yeah, that's why it looks like this. Minus e to the 1 over x. Oh, and then it's there we go. It's the same thing. So it's minus e to the positive 1 over x x squared. Okay. And the 0, this drops out. Down here we have negative x squared. So we ultimately end up with the limit as x goes to infinity of e to the 1 over x, which is this actually will be e to the 0, which is 1. Okay, remember, when you take the limit as x goes to infinity of 1 over x, that converges to 0. So we end up with e to the 0, which is just 1. Now, if you felt so inclined, anyway, it looks like we've already got the symbol Avogadro, so we don't need it anymore. Now, L'Hopital's rule is more flexible than it might sound because it also can be used if we end up with infinity over infinity. Okay, so it's not available for every one of these bizarre cases, but it's available for this one as well. So far we've seen that it works with 0 over 0 and infinity over infinity. Now, this one looks pretty innocuous. The only problem is if you directly plug in infinities here, oh boy. Well, what do we do now? All right. Now, by the way, if you could factor this, if let's say the numerator contained a factor which is in the denominator, we might be able to simplify it and avoid all this. But because direct substitution leads to infinity over infinity, we may as well go ahead and use L'Hopital's rule. Now, luckily here, these are two very simple functions. Using the power rule, you'll see that we're just going to wind up, man, look at this disaster. Yeah, we're just going to end up with 3 halves. Okay, again, because of the power rule. Okay, this goes to 3, this goes to 0, this goes to 2, and this goes to 0 when we take the derivative. So it's hard to see, but there's a horizontal asymptote there at 3/2. Now here's another one. Now the log of infinity is just infinity. 5x, that's going to infinity. So we can use L'Hopital's rule. And this is what it looks like. So if you remember, the derivative of log x, it's just 1 over x. And of course, the derivative of 5x based on the power rule is just 5. Okay. But now we're taking, oh, you know what? I shouldn't have done it like that. Hold on. Because it's actually, what I need is the limit. All right, let's try that again. So in other words, this could be rewritten as the limit after applying L'Hopital's rule, that is, of 1 over x over 5. But you recall, this one will go to 0. This one will just stay at 5. It's a constant. Until we end up with 0. And that just means if you look at this graph, this is an asymptote, horizontal asymptote. It doesn't look like it, but it's going to get closer and closer and closer to 0. Right. Now, there are other of these indeterminate forms besides these two. These are the ones that are eligible for L'Hopital's rule. You can get all kinds of crazy results. 0 times infinity, infinity minus 0, infinity to the 0 power, 0 to the 0 power. These are all the things that, yeah, drive mathematicians crazy. But sometimes they can be rewritten algebraically to turn them into this form, 0 over 0 or infinity over infinity. And then we can, of course, go ahead and use L'Hopital's rule. We're not just stuck. Okay. So here's an example. The 0 times infinity cases, this one, so we're assuming that this, let's say this goes to 0 and this is infinity. Well, what do we do now? Like this one. As this approaches infinity, this goes to infinity, but this one goes to 0 because the x is in the denominator. So, oh boy. Now look at this thing. um, Interesting. You might, that's a pretty interesting graph. So yes, well, you can factor out the 3, but you end up with infinity times 0. So now what should we do to rewrite it so that we end up with either 0 over 0 or infinity over infinity? And yes, so don't forget about these two. The limit as x goes to infinity is that 1 over x to the n is 0. But if we have the limit of x to the n as x goes to infinity, that's equal to infinity. Those are two important results. And so now, originally we had this. What we did was very simply move the 3x squared to the numerator. Now, what you can do now is this. So we basically divided the numerator and the denominator by x squared. In the denominator, I wrote it like this so you can see that this reduces to, I have to fix this. So you're going to wind up with the limit as x goes to infinity of 3 over 1 plus 1 over x squared. Now, the beauty of this is, as we saw here, no matter what the exponent of x is, as long as x is in the denominator, when we take the limit as x goes to infinity, we're going to wind up with 0. So that means we're just going to wind up with 3 over 1 plus 0, which is just 3. So we went from a catastrophic result, 0 times infinity, and suddenly it reduces to something very simple, which is just 3. Because we're able to rearrange this algebraically. In fact, we didn't even need L'Hopital's rule. We ended up with just 3 over 1, or just 3. So the reason why this worked is because we took advantage of these two definitions. Now, it's not always going to be possible to do this, but when it is, it's pretty satisfying to know that we found the way of reducing it to something simple. And so you can see this is the line x equals 3. This is our asymptote. And that's what you would have expected. No matter what's going on with the green, you can see that this red is the asymptote for that function. Now, what if we had divided by x instead of x squared? You wouldn't normally do that. But let's say you did for some strange reason. You're certainly allowed to do that. Direct substitution here would lead us to limit of 3 over 1 plus 1 over x. And let's see. Oh, no, sorry. What do we have here? Okay. So in other words, that you see, there's the rub. I just realized there's an algebraic error here. If you directly substitute now, you're going to end up with 3 times infinity over 1 plus 0, which means you did something terribly wrong. Now, here's an interesting one. So yes, the moral of the story here is that you don't want to divide by x in this case. You want the x squared. If you divide by x and you end up with a mess on your hands, then try something different. Now this one's slightly different. If you notice, this one has x cubed in the denominator. If we divide out, oh, this one worked out rather well. If we divide out by the x cubes, in the numerator we have 1 over x, in the denominator we have 1 over x cubed. Well, guess what? Both of these go to 0. So we end up with 3 times 0 over 1, which is 0. So I think what they're getting to here is that what you want to do is look for the highest exponent in the denominator and then divide everything by that. That's going to give you the highest probability of finding a form that you can use. Either you can now apply L'Hopital's rule or solve for it directly. And of course, anytime you find yourself making the situation worse, just go back and try something different. Now, this is an interesting one. This is the log of x times x. We can't approach it from the left because the function is undefined for 0. Log x is undefined for 0. But we can approach it from the right. You can see, as we approach from the right, function is going to negative infinity. The unfortunate thing, though, is that direct substitution is going to give us 0 times negative infinity, not what we were hoping for. And by the way, it's negative infinity here because, yeah, we're approaching from the right, and you can see that the function is going down to negative infinity. So what do we do instead? Ooh, now this is pretty clever. Log x over 1 over x. Algebraically, they are the same thing. Does that help, though? Um, oh boy. Now remember, we can now use L'Hopital's rule. The fact that the numerator is negative doesn't stop us from using L'Hopital's rule. Okay, it's still infinity over infinity. Even though one of them is negative, we can still use L'Hopital's rule. We'll apply that to the original function. And again, you remember that the log has a derivative of 1 over x. And the derivative of 1 over x, which is x to the minus 1, is minus x to the minus 2. So the ratio that we end up with is 1 over x over negative x to the minus 2, or we can rewrite it like this. And that actually reduces to negative x, okay, because we have see, that reduces to negative x squared over x, which is simply negative x. Now, when you approach 0 from here, you'll just plug in the 0 and you get 0, which is what we would have expected. So this L'Hopital's rule is going to be very, very powerful and flexible, especially given that if we don't have exactly the form that we need, we can often rearrange our limit algebraically to put it into a form that we can solve for directly or possibly apply L'Hopital's rule to. That's good to know. So whenever you run into one of these messes, first thing you think about is maybe rearranging it algebraically, and possibly you'll be able to solve it directly. Possibly you'll just be able to use L'Hopital's rule. Now, that doesn't guarantee that you'll be able to do one of those. I mean, there's still cases that you wouldn't be able to use this with, but it certainly increases dramatically the number of problems you can solve this way. Ooh, now like this one, infinity minus infinity. So it's hard to make a general statement about this one. It depends on how fast they're converging to infinity. Okay. So in other words, it depends. Like if you have a function like this, as x goes to infinity, the function is also approaching infinity, but very slowly. And then you have something like this. Well, it's going very quickly. So it matters a great deal which is which. All right, so here's a couple of cases. We've got f of x is 3x cubed. G of x is 3x squared plus 5. So we want to find the limit of the difference as we approach infinity. So you can see when you've done all the algebra, we end up with this polynomial. And we know that this one solved directly gives us infinity. Well, now what do we do? Oh boy. Well, the way we look at it is this. Because this term is positive. This is this is x cubed. This is, oops, sorry. This is 3x squared. X cubed would look 3x cubed would look something like this. So because this comes first, and this is just a constant, that means we can conclude from this that even though it's infinity minus 5, the difference between the two is approaching infinity, not negative infinity. Okay, so we end up with infinity because the larger one is the smaller one is being subtracted from the larger one. I shouldn't say the smaller. The one that's approaching infinity more quickly is here. So therefore, the difference must be approaching positive infinity. Now here we've got it back. Oh, wait, no, we don't. We've got two that appear to be tied, but it doesn't make any difference because the x terms drop out and we end up with -5. Huh. Okay. And then now look at this one. Now this time we have the slower, this one is a linear function. So it's approaching infinity more slowly than this one. When you plug in all those numbers, you can see as we approach infinity, we have infinity, minus 5 again, like we had before. But now the slower converging function is first. And so we end up with negative infinity because the difference between them will keep getting smaller and smaller, and it will approach negative infinity. Huh. So here's a wacky one. Infinity raised to the 0 power. So what they're encouraging you to do here is use the properties of logarithms to rewrite this. So like, for example, here, we're going to rewrite y as x to the 1 over x power. So based on the properties of logs, remember, we're going to rewrite this as 1 over x log x, or log x over x. So when we take the limit, now the limit of the log as x goes to infinity is infinity. And this one is also infinity. So that means we can use L'Hopital. Which is easy because the limit, the derivative of log x is of course just 1 over x. The derivative of x is just 1. So we end up with the limit of 1 over x over 1. But of course, this, as we saw earlier, goes to 0. So the final result is 0 over 1, which is just 0. Wow. So basically, the logic here is that there's a lot of different limits you might run into with these strange results. And so what we need to do is get into the habit of looking for opportunities to use L'Hopital's rule. And when not, we want to look for opportunities to rearrange them algebraically until they do fall into that category, hopefully. If not, there are other techniques we can use that we haven't looked at yet. All right, so that was 3C. Let's just do a coming attraction for D. Now, I mentioned this a couple of times. Chapter 4 is basically, it's called integrals. The word antiderivative and integral both mean the same thing. What we're effectively doing is reversing the process of differentiation here. And so here we're going to get a taste of that, just a taste, so that then when we go into 4, we'll have an idea of what we're trying to do. Now, unfortunately, from your perspective, integration is typically more challenging than differentiation. There is a chart in the book, though, that I'll show it to you next time, that will help us. It's an enormous list of all these different integrals you might run into. And having a chart like that is going to be a huge help to you because there's so many possibilities. And but we'll save that discussion for next time. It's let's just say it's better that we talk about it next time. All right. So you'll see. I mean, it's takes a little getting used to what we're trying to do. But the only unfortunate thing is that there's a lot more messy cases that we might encounter than when we take derivatives. Okay. So, and you'll notice in the book that it gets an entire chapter all to itself. Okay. So anyway, I'll see you all next time.